Hello everyone, welcome to the course Fundamentals of Manufacturing Processes. In week 12, we'll talk about surface modification processes. So this course is offered by Professor D.K. Dwivedi from Department of Mechanical and Industrial Engineering, IIT Roorkee. I'm TA Alka Jangid, from IIT Kanpur. So firstly, we'll be going through some sample assignment questions which will help you in solving your weekly assignments, and then we'll go through some lecture notes. Okay, so first question is, during the tempering process, the temperature of the steel reaches up to, your options are below 650 degrees Celsius, 750 to 850 degrees Celsius, 1120 degrees Celsius to 1150 degrees Celsius, 1200 degrees Celsius to 1300 degrees Celsius. So for answering these type of questions based on all heat treatment processes, you need to keep in mind the lower critical temperature of steel. Okay, so it's around 723 degrees Celsius. So above that, you'll be performing annealing and normalizing processes. Tempering will be below that. So tempering is done at very lower temperatures compared to lower critical temperature. So correct answer will be below 650 degrees Celsius. And you need to keep in mind the definition of tempering as well. So tempering is basically done to relieve the residual stresses that arise during formation of martensite. Okay, after quenching, there will be a lot of residual stresses. So tempering is a heat treatment process which improves the properties of steel by heating it to a temperature below its lower critical temperature and then cooling it gradually in the air. So purpose is that it increases toughness, it reduces brittleness and improves machinability, and it's often used on metal products that will be under a lot of stress, such as bolts, nuts, screws, washers and knives. Temperature, the tempering temperature of steel can vary depending on the steel grade and the desired properties, but is typically between 160 and 600 degrees Celsius. Low temperature tempering is carried out between 150 to 200 degrees Celsius, which produces high strengths, while high temperature tempering, it will be, so as you go above at higher temperatures, you will be converting to the phases which are more near to the equilibrium phases. So those will be having lower strength and lower hardness. Okay, so high temperature tempering is carried out at 500 to 650 degrees Celsius, and this produces microstructures which will be coarser in nature. Tool steels are tempered between 200 to 300 degrees Celsius. Spring steels are tempered between 300 and 400 degrees Celsius. Structural steels are tempered between 450 to 650 degrees Celsius. Now this process involves heating the steel to a high temperature and then allowing it to cool in the still air. The cooling rate and method are important and usually involve cooling in air. In fact, the tempering process changes the steel's microstructure, which can affect the type, size and amount of carbides that are found. Next is two-staged quenching of steel is carried out in the process called, your options are annealing, normalizing, mar tempering and os tempering. So two stages quenching is done in case of mar tempering. Okay, so this is the cooling curve for the mar tempering. So firstly your cooling, so your core and surface of the center and surface of the sample both will be having different cooling rates. Okay, because the surrounding area surrounding environment is different for center as well as for surface. So surface will cool faster compared to center. So before MS, it is held at that particular temperature and then it's quenched, so that the temperature is uniform throughout the surface and center. Okay, then transformation takes place and then it's tempered if desired. So the process of quenching steel in two stages is called tempering, and it is also known as stepped quenching or interrupted quenching. In this case, steel is heated above its critical temperature and steel is quenched in a hot medium such as molten salt, hot oil or molten lead at a temperature of 150 to 300 degrees Celsius. Cooling, steel is then transferred to a less intensive medium such as air or oil and cooled completely. Tempering helps to increase impact strength, increase wear resistance, increase hardness, reduce the risk of distortion and reduce internal stress. Next question is, which of the following is true regarding the surface modifications? Your options are: the characteristics of the surface are different from the base metal, increasing the life cycle of the component, or improved functionality of the component, or all of these. So correct answer will be all of these. So surface modification is a technique which changes the surface sorry. So surface modification is a technique which changes the surface of a material to improve its properties or function. And there are several different surface modification techniques, which includes plasma functionalization. It is a single step process which changes the surface chemistry of polymers to improve their properties. Then chemical modification. It is a technique which focuses on the surface chemistry to improve the absorption of contaminants. Next is chemical vapor deposition, CVD. It is a technique which deposits a solid layer of compounds on a surface by carrying out chemical reactions in a gaseous medium. Next is coating. So a widely used technique that compresses the outer surface of a material to make it more resistant to breakage. Then ion implantation, a technique that impacts accelerated ions into a solid surface to change its chemical or tribological properties. Next is physical modifications, a technique which changes the topography or morphology of a surface without changing its chemistry. Now, surface modification techniques can be used in various fields including biomaterials, membranes and implant biomaterials. Next question is, which of the following are the processes which are used for the coatings to preserve or improve material functionality? Your options are hot dipping, cladding, electroplating or all of these. So the correct answer will be all of these. So schematics are shown for hot dipping. So here your steel part will be dipped in molten zinc, and electroplating, here because of the potential difference on the cathode you would be depositing some metal. In case of hot dip galvanizing, it involves dipping a metal object into molten zinc to create a thick coating which is resistant to corrosion. This process is suitable for larger objects. Electroplating, it involves depositing a thin layer of metal onto an object using an electrolytic solution, and this process is better suited for smaller objects or those that require decorative finishes. Then cladding, it is a welding process which involves applying a layer of weld metal to a base metal surface to improve its corrosion and wear resistance, and it's also known as weld overlay, corrosion resistance alloy, weld overlay, or hard facing. Next question is the relation between carburized thickness and the time in the carburizing process is expressed as. Your options are: thickness is directly proportional to the time, thickness is inversely proportional to the time, thickness is directly proportional to the square root of time, and thickness is directly proportional to the cube of time. So the correct answer will be C. Okay, so this is the formula that is given here. Case depth is equals to K times under root T. Here K is the constant, T is the time. So carburizing is a heat treatment process which makes iron or steel harder and more wear resistant by absorbing carbon. And this process is in carburizing, it involves heating the metal in the presence of carbon bearing material like carbon monoxide or charcoal at temperatures between 850 to 1000 degrees Celsius. Its benefits: so carburizing creates a hard protective exterior while keeping the interior relatively soft. This combination of hard exterior and soft interior makes carburized steel useful for manufacturing intricate metal items like internal machine components. Process steps: so carburizing often ends with the quenching the metal in a liquid to rapidly cool it and then finalize the hardening process. And for a given steel at a given temperature, the depth of penetration is dependent on diffusion and can be related to the time T by this equation. Here K depth is equals to K times root T, where K is constant and T is thickness. T is time. Next question is: the process of surfacing offers maximum metallurgical bond strength with the substrate is. Your options are cold spray, HVOF spray, flame spray, or all of these. And correct answer will be cold spray. So cold spray is the surface modification process which creates a metallurgical bond with a substrate, and its working involves a solid powder particles are accelerated at supersonic speed and hit a substrate at temperatures below the melting point, and the particles deform plastically and stick to the surface. Benefits are: cold spray has several advantages over other thermal spray methods, including lower oxidation, less porosity, no phase transitions, no residual thermal stresses. And materials: cold spray can be used on a variety of materials including metals, polymers, ceramics, and composites. Applications: cold spray is used for localized repairs and additive manufacturing. And here we can see the technique of cold spray. Okay, here heat helps compress to the supersonic velocities. Next is the arc spraying method results in a melted base metal depth of 3 mm and a surface layer depth of 2 mm. The dilution level ratio is. Your options are 0.2, 0.67, 1.5 and 0.6. And here on this you can see there are depth of the substrate, melted base metal, and then on top you have surface layer. So you have to find the dilution level ratio. So correct answer will be 0.6, and the dilution level ratio can be given as depth of melted substrate upon depth of melted substrate plus depth of the surface layer. So the combined will be 3 plus 2, it will be 5, and the upper depth of melted substrate is given as 3. So 3 by 5 will be 0.6. Next question is, which of the following processes causes surface layer deformation to improve the surface properties? The options are short peening, sandblasting, and nitriding. So options are 1 only, 2 only, 1 and 2, or 1, 2, 3 all. So correct answer will be 1 and 2. So these are the definitions for all these three processes. So which of the following processes causes surface layer deformation to improve the surface properties? So out of these, nitriding doesn't require surface deformation. In this case, you change the chemistry of the surface by introducing nitrogen atoms. So in case of short peening, a cold process which uses steel balls to compress the surface of a metal, and this process is used to improve fatigue strength and can be used in the aerospace, automotive, and construction industries. Short peening is different from short blasting, which is used to clean or prepare metals. In case of short blasting or sandblasting, sometimes known as abrasive blasting, is the operation of forcibly propelling a stream of abrasive material against a surface under high pressure to smooth a rough surface or to roughen a smooth surface, to shape a surface, or to remove surface contaminants. It uses sand particles to remove material from a surface. Sandblasting is often used to prepare a surface for painting or coating. In nitriding, a surface hardening process which introduces nitrogen atoms into a ferrous alloy. And there are multiple nitriding processes including gas, plasma, and salt bath nitriding. Next question is, step cooling in carburizing thermal cycle helps in reducing. Your options are tensile strength, hardness, cracking and distortion tendency, or all of these. So the correct answer will be cracking and distortion tendency. Okay, so in a carburizing thermal cycle, lowering the temperature of a part before quenching reduces thermal stress and quench distortion. This is because overheating, quenching directly from the carburizing bath. So if you are quenching directly from here, it can overheat the surface layer, which can lead to the lower surface hardness. And retained austenite, if the retained austenite is too high, the part may need to undergo a sub-zero treatment to transform it into martensite. Carbon content, if the carbon potential is constant, the carbon content and hardness of the part may drop quickly in the case, and this can lead to a soft surface that can't be used. Okay, so here is step cooling is used to prevent all these distortion and other defects. And after that you require tempering so that the martensite or some residual stresses can be relieved and martensite can be converted into more stable structures. 10th question, the range of flame temperature required in the HVOF thermal spray process is. Your options are 1000 to 1500, 1500 to 2000, 3000 to 3500, 10,000 to 15,000 degrees Celsius. So the correct answer will be the So the maximum gas temperature in the high velocity oxygen fuel thermal spray process is typically 3000 Kelvin, and the powder particles are exposed to a flame in the combustion chamber, which melts or semi melts them. The particles then enter high pressure stream for spraying onto the substrate. The spray methods are flame, electric arc, HVOF, HVAF. So HVAF is high velocity air fuel and HVOF is high velocity oxygen fuel. So temperatures for these processes is 3000, 4000, 3000 and 2000 to 3000, and particle velocities keep on increasing in this order. So it is 40 in case of flame, it is 100 for electric arc, it is 600 to 800 for HVOF and 600 to 1200 for HVAF. Next is heat treatment and tempering. So this is how heat treatment is defined. So heat treatment consists of heating the steel part or any other metal. So it's first heated to a particular temperature, then at that particular temperature it is held at that particular temperature for particular time, and this is also known as holding or soaking. Then after that it is cooled in a controlled cooling rate, and it is done to obtain desirable mechanical properties such as better machinability, improved ductility and homogeneous structure, and also for desirable conditions such as relieving internal stresses. These are various purposes for the heat treatment. So heat treatment causes relief of internal stresses developed during cold working, welding, casting, forging, etc. It also can harden and strengthen metals, it can improve machinability, it can change the grain size. For example, in normalizing, you get the grain size which is lesser than initial grain size. Soften metals for further cold working, as in case of wire drawing or cold rolling. Improve ductility and toughness. Increase heat, wear and corrosion resistance of materials. Improve electrical and magnetic properties. Homogenize the structure to remove coring. Spheroidize tiny particles such as those of Fe3C in steel by diffusion. Next is fundamental diagrams. So these are three diagrams that are required in understanding heat treatment processes. First is iron carbon phase diagram, then time temperature transformation diagram, and continuous cooling transformation diagram. So this is the iron carbon diagram and the iron carbon diagram, because here it is shown up to Fe3C and the temperatures are corresponding to the iron carbide diagram. Okay, because Fe3C is forming, if it would have been graphite formation, then it would have been iron carbon diagram, and those requires more equilibrium conditions compared to this. So here in iron carbide diagram we can see three equilibrium, three reactions that will be taking place: eutectoid reaction, eutectic reaction and peritectic reaction. So in case of peritectic reaction, delta and liquid they convert into austenite. In case of eutectic, liquid converts into gamma austenite plus Fe3C. In case of eutectoid steel or eutectoid reaction, austenite converts into mixture of ferrite and cementite. Okay, and the temperatures also you need to remember. So for eutectoid reaction it is 727 degrees Celsius, and for eutectic reaction is 1147 degrees Celsius, and for peritectic reaction it is 1493 degrees Celsius. And this plot shows the temperature ranges for full annealing and normalizing and spherodizing annealing. So spherodizing annealing is done below lower critical temperature. So this line which corresponds to this eutectoid line, it is lower critical temperature, and this line between austenite and this region, it is known as upper critical line. Okay, so A3 is upper critical. So this full annealing is done in this range and normalizing is done in this range. Next is time temperature transformation diagram or isothermal transformation diagram or iso temperature diagram. So in this case you can see there are two C curves. So in this region, you have metastable austenite. Okay, so below this eutectoid temperature you have metastable austenite in this region. Here the reaction will take place in between these two C lines. So here you have pearlite in upper region and bainite in lower region, and here you'll be having converted pearlite or bainite. And below this MS temperature you see formation of martensite, and MF temperature will be for complete formation of martensite. So if this cooling curve it comes without going in this region, then you will be having with the very faster cooling rates, then you will be getting martensite formation. Okay, so these are four different cooling curves are shown. So fourth one shows formation of pearlite. Okay, so in this one you have fine pearlite. In case of 3, it's going here and converting into 50% bainite, and then remaining will be converting into martensite. 2 corresponds to formation of martensite. 1 corresponds to martensite and some retained austenite. So below MS temperature you will be having austenite that will be in form of retained austenite. Next is continuous cooling transformation graphs. So here the graphs, the cooling curves will be continuous, so they won't be having this isothermal type of cooling. Okay, so it won't be kept at a particular, it won't be held at a particular temperature for the transformation. So these are continuous cooling diagrams. So in these diagrams it is very it can't be formed in form of bainite, because bainite will come below nose temperature and you are cooling continuously. So this one will be having pearlite, and this one will again have fine pearlite. Okay, so if it doesn't touch this nose temperature and it comes from this side, then it will be having martensite. These are the heat treatment processes: annealing, normalizing, tempering, hardening and carburizing. And the temperature ranges for holding temperature is also given. So for normalizing and full annealing and hardening we already saw. Spherodized annealing also we saw. Process annealing is done in this region and up to 0.2 carbon % composition. Next is annealing. So annealing is performed to reduce hardness, improve machinability and facilitate cold working and produce a desired structure. Some of the types consist of full annealing, critical annealing, process annealing, spherodizing, and stress annealing, stress relieving. Okay, so the temperatures are also given for all of these processes: full annealing, normalizing, and spherodization, recrystallization annealing, stress relief annealing, all below A1. Next is normalizing. So normalizing of steel is carried out by heating above upper critical temperature and soaking there for some time and then cooling in the air to room temperature. The aims are to improve hardness and strength, to improve machinability, and to modify grain structure, and also to provide more consistent response when hardening or case hardening. So this is the normalizing temperature region, and the terminology used for steel below 0.8% carbon, it is hypoeutectoid steel, and if above this carbon percent is above 0.8%, then it will be hypoeutectoid steel. Next is tempering. So tempering is carried out by heating the steel below lower critical temperature and held for a period and then slowly cooled in air to room temperature. And here you can see, with increasing tempering temperature, elongation basically increases, so toughness increases and hardness reduces. And this is the cycle used for hardening and tempering. So firstly, steel is heated and then austenizing. For some time it's given time for austenizing, so austenite is formed, then it is quenched, and after quenching there will be martensite formation. So martensite is metastable phase, so for that it is heated and tempered, then air cooling. So after this, your martensite converts into more stable structures and more fine structures, which will be having better properties compared to martensite and retained austenite. Next is post-tempering and mar-tempering. These processes have been developed to avoid residual stresses generated during quenching. And in both these processes, austenized steel is quenched above NMS, say to a temperature T1, for homogenization of temperature across the sample. In mar-tempering, the steel is then quenched and the entire sample transforms simultaneously to martensite. This is followed by tempering. Okay, so here before reaching to MS, it is held for some time so that the core of the sample and the surface of sample, they both reach at the similar temperature. Then it is quenched, and after that it is provided some tempering. Okay, in mar-tempering, steel is then quenched and the entire sample transforms simultaneously to martensite, which is followed by mar-tempering. In aus-tempering, instead of quenching the sample, it is held at T1. So T1 it is held for very longer time, for then entire this metastable austenite, it transforms into bainite. Okay, so instead of quenching, it is held at T1 for it to transform to bainite. Next is hardening. Okay, so in this case the sample is heated above A3 or ACM, depending on the type of steel, whether it's hypoeutectoid or hypereutectoid. So after it causes austenization and the sample is then quenched at a cooling rate which is higher than the critical cooling rate. Okay, to avoid the nose of the CCT diagram. and the quenching process produces residual strains, thermal and phase transformation. The transformation to martensite is usually not complete and the sample will have some retained austenite. The martensite produced is hard and brittle, and tempering operation usually follows hardening, and this gives a good combination of strength and toughness. Next is improving surface properties introduction. So these are various processes and these are plotted in for understanding the thickness of layers. Okay, for in this case the thickness or subsurface depth of surface, where A is ion implantation. So A has the lowest thickness range, lowest thickness size, and then after that we have PVD, then we have CVD, then we have electrolytic plating, electroless plating, hot dipping, which also known as galvanizing or aluminizing based on material used. Then we have laser surface alloying, then we have transformation hardening, then we have mechanical working, nitriding, carbonitriding, carburizing, thermal spraying, friction surfacing and weld overlays. These are various processes and the thickness is keep on increasing in this order. Based on these various processes, so these are various zones that are formed. So upper zone, then below that you have zone 2, then zone 3 and zone 4 will be having a very refined microstructure because of the partial melting that may be taking place. Then we have zone 5 which doesn't have any effect. Now various properties that are altered in case of these surface modification processes. So first is physical properties. So thermal conductivity of material, thermal insulation, thermal expansion coefficient, refractoriness, density, optical properties, which can be absorption or reflection of radiations. These can be altered. In case of chemical properties, so chemical affinity and corrosion oxidations, these can be altered. Next is mechanical properties. In this case, hardness, strength, ductility, fracture toughness, bond strength, residual stresses, stress corrosion cracking, hydrogen embrittlement. All these properties can be altered. Dimensional properties such as straightness, flatness, roundness, surface roughness, length, etc. These also depend on the final heat treatment or the surface modification process that is applied. Now surface modification methods, they can be of two types. One in which you change surface structure or control deformation. So in this case there is no chemistry change. So first is thermal based, in which you can use flame, induction heating, laser, electron beam, plasma or TIG arc. These all can be used for heating only the surface of the steel. So after heating this, it is cooled very fast, so it will be forming structures which will be very high, having very high hardness. In case of mechanical, we have short peening and burnishing. So the surface of material is deformed with these blasting of shots or other processes, which leads to introduction of some compressive residual stresses near the surface. It improves the fatigue properties of the products. Next is change surface structure and chemistry. So chemical methods at high temperature. So first is diffusion. In this case, carburizing, nitriding, carbonitriding, boronizing and vanadizing. These are the processes where these elements will be diffusing near the surface metal. Ion implantation, where nitrogen and other elements they can be used. Alloying, laser, TIG and plasma. Surface modification methods, where developing a surface layer. So these can be diffusion based, where CVD and PVD is used. Melting, so here weld surfacing or laser cladding can be used. Hot dipping, zinc, chromium, aluminum, lead, tin, these can be plated by using dipping. Electrolysis, so in this case chromium and nickel can be plated and it helps with the aesthetics. Cadmium and zinc for controlling corrosion. Copper and Ag for improving electrical properties. Hard chromium for enhancing wear resistance. Mechanical methods such as roll bonding or explosive bonding. Change in surface structure. So in case of mechanical method, based on localized plastic deformation and so work hardening of near surface layers such as burnishing and shot peening. In case of thermal methods, these are based on localized heating and controlled cooling to obtain desired microstructure. The flame and induction hardening, laser and electron beam hardening, plasma and TIG melting. Now this is the process comparison based on process complexity and technology level. So as you keep on going in this side, you will be seeing the process is becoming more complex and more advanced based on technology. So burnished films has the lowest complexity and lowest technology level. And then there is resin bonded coatings, then induction and flame hardening, then we have carburizing, nitriding and anodizing. After that we have laser cladding and dispersion coating, and then pulsed plasma nitriding. Then we have physical vapor deposition and chemical vapor deposition. Scope of surface engineering. So these are various areas that explore surface engineering. So how to develop modified surfaces, designing modification that is desired, applications of engineered surfaces in this field, and investigating modified surfaces. These are some of the fields that all fall in surface engineering. Next is improving surface properties, surface modification processes. So one of the process is mar tempering. It is part of heat treatment. So in this case it is a heat treatment process for steel which involves quenching and tempering to achieve a uniform temperature throughout the material. And in this case the steel is heated above its upper critical point, and the steel is then quenched in a hot bath of oil, molten salt or molten lead, and the quenching temperature is slightly above the martensite start temperature. The steel is held in the quenching medium until the temperature is uniform throughout. Okay, the steel is held in quenching medium until the temperature is uniform throughout. Here you can see the center and surface at different temperatures, then it is held at that particular temperature, so that temperature reaches uniform uniformity. Then it is quenched, and then after that tempering is required. The steel is cooled in still air at room temperature. Bar tempering is also known as stepped quenching or interrupted quenching, and it's used to minimize distortion, cracking and residual stress. Bar tempering is well suited for high quality steels, bearings, gears, tooling, dies and shafts. Bar tempering is more expensive than other quenching or tempering processes because the quenching oils need to be specially mixed. Next is tempering, which is a heat treatment process which improves the mechanical properties of ferrous metals. And like steel and ductile iron, it's used to increase strength and toughness and to reduce or eliminate distortion. This process involves heating the metal to a temperature which produces austenite, holding it for a period of time and then rapidly cooling it to a temperature above the martensite start temperature. The tempering produces a bainite microstructure in steel and an acicular ferrite and osferrite structure in cast iron. Tempering is an isothermal process, so the transformation happens over time, resulting in uniform growth and less distortion. And this makes it possible to design the dimensional change into the component. Tempered parts are ideal for use in systems that are under frequent stress, such as springs, clips, seatbelt loops, agricultural components, lawnmower blades and mining, oil and gas components. So here you can see the cooling curve for the tempering. So here the temperature on surface and center are different, and then after holding at a particular temperature this becomes uniform, and after this transformation the metastable austenite converts into bainite. This process is more economical compared to the formation of martensite and then followed by tempering. Next process is shot peening, which is a cold working process which uses high speed spherical particles to improve the surface of metal components. In this process, a stream of small spherical particles, which are called shots, are fired at the metal surface at high speed, causing plastic deformation. Its benefits are that it improves fatigue performance, it increases resistance to stress corrosion, it provides shape or strength, it straightens the flat metallic parts, and it reduces component weight while maintaining mechanical strength, and expose and eliminate hidden corrosion. Its applications, so it is commonly used as on components like gears, springs, aerospace parts, drive shafts, crankshafts, connecting rods, steering and gear parts, and turbine blades. Some of the risks, so there is risk of weakening the component or reducing fatigue and bending strength, and the test procedures, they have been introduced to prevent these risks. So here you can see with this shot, it is at a particular speed which will be hitting the component, and it will be leaving some dimples of the at this metal. So after a lot of shots will be moving at a high speed, then there will be formation of very smooth surface, and here formation of compression will also be there, which will be improving its fatigue properties. So how this shot peening works, here the shot acts like a pin hammer and dimpling the surface and causing compression stresses under the dimple. The surface compression stress strengthens the metal. Next is sandblasting. So sometimes known as abrasive blasting is the operation of forcibly propelling a stream of abrasive material against a surface under high pressure to smooth a rough surface and roughen a smooth surface, or to shape a surface, or to remove surface contaminants. And there are several variants of this process using various media. Some are roughly abrasive, whereas others are milder. The most abrasive are shot blasting with metal shot and sand blasting with sand. Moderately abrasive variants include glass bead blasting with glass beads and plastic media blasting, which is known as PMB, with the ground up plastic stalk or walnut shells and corn cobs. The sand blaster components. So a sand blaster has a blast pod that holds the abrasive material and an air intake that's powered by a compressor. Abrasive material. The abrasive material can be sand, glass, plastic, metal, or walnut powder. In case of sandblasting process, the compressor applies pressure to the abrasive material in the blast pot, which is then forced through a valve and out of the nozzle at a high speed. So in case of surface impact, the abrasive material impacts the surface with force, removing debris, paint and other contaminants, and improves the surface finish. Sandblasting is used on a variety of materials including metal, plastic and wood, and it's often used to prepare a surface for painting, epoxy or powder coating. Next is improving surface properties, changing chemical composition. Here overview of processes, purpose and design. So these are various modification processes. First is carburizing and plasma carburizing. Here the element that's used is carbon and the mechanism that works is diffusion. So through diffusion, carbon will be going in the surface area of the component. Okay, so what happens with as the carbon will go in the surface region, so there is more chances of formation of martensite in the surface area. So it becomes hard at the surface while the core part will be having more tough region. Next is nitriding and plasma nitriding. So in this case you have nitrogen and the mechanism used is again diffusion. So with the diffusion, nitrogen will be introduced in the surface region, and in case of nitrogen it provides higher strength compared to higher hardness compared to carbon, the nitrides that are formed. Next is cyaniding, carbonitriding and nitrocarburizing. In this case the elements used are carbon and nitrogen both, and the mechanism used is diffusion. In case of boronizing, you have element used is boron and the mechanism is diffusion. Next is laser, plasma and TIG alloying. So here the elements that are used are chromium and nickel, and the mechanism used is melting. Then we have ion implantation. In this case elements used are ions and the mechanisms are damaging crystalline structure. Okay, so hardness versus processes. So hardness of steel and titanium carbide is given for the comparison. Here, as you keep on changing these various processes, so lowest having will be carburizing, then higher than that you have carbonitriding, then you have nitriding at the highest strength among these three, then boronizing has the higher than these three processes. It's up to here 1800 HK. Okay, now this is general approach. So here outside you have requisite element, which is requisite element rich environment in plasma, ion or vapor forms. Here the options are nitrogen, chromium, carbon, boron or silicon, and this is the substrate which is rich in these elements. Now in case of carburizing, you have formation of a carburizing layer, and the concentration of carbon will keep on decreasing as you move away from the surface. So case depth is decided based on this particular composition. Okay, and the matrix is ferritic matrix, which will be tougher in nature, while the surface will be having with high hardness and strength. And here you can see with different temperatures you get different carburizing depth compared to carburizing time. So at higher temperature there will be depth will be higher compared to at lower temperature, because diffusion will become faster. Next, with increasing carburizing depth, you can see various properties how they will change. So hardness will keep on decreasing as you move away from the surface, and you keep on increasing the depth, and carbon percent will also keep on reducing, while residual stress firstly it decreases, then it increases. So the residual stress won't be highest at the surface, but it will be lowest near the surface. This is the carburizing process. So here heating chamber of steel is shown. So here you can use various carbon sources. So some of the examples include activated charcoal, and other is carbon monoxide gas. So here parts are kept which are to be carburized, and then they are covered with the sources of carbon, and then time for diffusion is given. And this is the thermal cycle for carburizing. So first it is heated to temperature higher than 800 degrees Celsius, then soaking is provided. So after austenization, because at austenite temperature you have more solubility of carbon, so here it is exposed to the carbon, then after that it is cooled with step cooling. Okay, step cooling, why we require step cooling? So I told during a question as well. So step cooling reduces the distortion that will be if you will be cooling directly from this point, and after quenching you require tempering as well, because martensite need to be converted into more stable phases and to reduce the residual stresses. Next is nitriding. So based on different alloys that you use, the case depth at a particular time is different. For example, this nitra alloy, it dissolves more nitrogen and it has higher case depth compared to AISI 4140 and AISI 4340. Okay, and nitrogen concentration can be seen, it will keep on decreasing as you keep going further from the surface. And this is the various uh, this is the chemistry of the component after nitriding. So near surface you will be getting epsilon nitride, and after this you will be getting this gamma nitride, and then you will be having nitrogen which will be dissolved in alpha iron. Okay, so this is the compound formation and this is the diffused nitrogen zone, and this is the component which doesn't have any effect of the nitriding. Next is plasma nitriding or carburizing. Okay, in this process, plasma based processes that require active carbon and nitrogen atoms which are obtained directly through plasma formation under controlled conditions of temperature from 300 to 800 degrees Celsius and pressure which is kept between 300 to 1000 Pascal. This is the chamber that's used. Here you have atoms of the, you have job and the atoms of carbon or nitrogen, and the process gas mixture which is of methane, propane, hydrogen and argon, and this will be providing with the required carbon. Okay, and these are various zones that are there. So there will be dark zone, there will be white zone, and there will be substrate based on the microstructures that are present. Next is laser alloying. In this case you have substrate and elements that are pasted over the substrate. Okay, so this is just the paste, it doesn't have any bonding between this of chemical or mechanical type, and then this laser beam is directed on the substrate. So this is moving in this side. So this part is already solidified and this part is melted and this part is yet to be melted. Okay, so here laser will melt, the laser melts of elements and substrate, and the solidification results in alloyed surface. So there will be some atoms will be combined with these elements and will be forming alloy on the surface. Okay, so here you can see nickel phosphorus coating on the substrate. In case of laser alloy you also have columnoid 88, and this is on turbine blade steel. So here you have 14 chromium and 4 nickel, this type of alloy. Next we have ion implantation. In this case ion beam is used and evaporator will be providing with vapors, and here this ions will act and destroy any crystal structure that is present on the surface. So this destroyed crystalline structure, damaged lattice structure, will be providing it with some unique properties, mechanical and chemical. So this is of use. So in this region you have unaffected substrate which will be having perfect crystalline structure. Then you have boronizing. In case of boronizing, it increases hardness of the order of 1500 to 2000 VHN up to a depth of about 50 micrometers, and the boron is introduced using boron carbide pack cementation or gas boronizing process, which involves high temperature up to 900 degrees Celsius and exposure for about 6 hours. So here you can see boron concentration will keep on decreasing as you move away from the surface. And near surface we can see there is iron Fe2b type of compound formation, and below that we have Fe2b type of compound formation because it is iron rich layer, and this is the steel substrate. So there are various layers that are formed of Fe2b, then combination of Fe2b and Fe2b, then you have Fe2b and then Fe plus Fe2b. Last chapter is improving surface properties using coatings. So first process is galvanizing. In this case, hot dip galvanizing is essentially a brazing process, and the steel is cleaned, in which case mechanically and chemically cleaned, and then heated to 850 Fahrenheit in a molten zinc bath. The molten zinc reacts with the surface of the steel and forms a coating of various layers of zinc and iron alloys, it depositing a layer of material that is approximately 40% pure zinc. Then we have galvanized coating. So here these are various structures that are formed. You have base steel having 159 hardness, then you have gamma having 75% zinc and 25% iron, having higher hardness compared to base steel. Then you have delta having 90% zinc and 10% iron. You have zeta, which is 94% zinc and 6% iron. Then you have eta having 100% zinc. So here you have thermal spray coating as well. So there are two types of galvanizing, dry galvanizing and wet galvanizing. In case of dry galvanizing, you have casting cleaning, then rinsing, then pickling and rinsing, flux solution, drying, then it is dipped in zinc bath, and then after that cooling and inspection. In case of wet galvanizing, initial part is same up to rinsing part, then the dipping is done with the help of flux, and then cooling is done. Then we have thermal spraying. In this case, material feedstock is present, so it can be in form of bars or in form of particles. Okay, then it is with the help of heat source, it is accelerated droplet. Okay, and this droplet will be going on the substrate and will be forming this type of coating. Twin wire arc system. Here you have two arc wires and it is connected with the help of this DC power supply, and it is used for forming coating. This is the twin wire arc system. Now we have coating process versus thickness. So here thickness is 100 mm and it is keep on reducing in this side. Okay, so highest will be in these welding processes having size in 10 mm, around 10 mm. Then we have carburizing, nitriding, spray fuse, flame spray, plasma spray, and electroless, nickel plate, all these spraying processes. Then we have chromium plating, CVD, with reducing thickness. And we have PVD. Okay, then vacuum coating, iron plate and sputter coating, and iron implantation with reducing thickness and depth. Next are these three approaches for the formation of these films. So first is flame sprayed, then chromium plating and HVOF coated, and this thickness is different. So in case of chromium plated it is around 50 micrometer, while here it is 250 micrometer. Schematic of thermal spray process. So here you can see this gun will be providing the spray stream, and here it will be forming a layer on the substrate. So here three stages. Firstly, generation of thermal or kinetic energy, and then second is interaction of this energy with the spray material, then interaction of spray particles with the substrate. In case of spray stream, we have flame, plasma, etc. Then we have composition, temperature, velocity, spray distance, external environment, turbulence. These are various parameters to take care. In case of gun, we have nozzle geometry and power, gas flows, gas composition. These are various parameters. In case of material feed, you have particle size and shape or wire size, you have feed rate, you have injection method and geometry, you have carrier gas, flow and velocity, have chemical and physical properties. In case of substrate, we have surface contamination, you have surface profile, you have temperature, chemical and physical properties, and relative speed to gun. Now these are the schematics shown for various thermal spray processes. Now comparison of thermal spray processes. So these are various parameters. So in case of form of coating material, so in case of flame spraying, you have coating material in form of either powder or wire. In plasma spray, you have it in form of powder, and in HVOF spray also you have it in form of powder. In case of heat source, in flame spraying it is in oxy-fuel combustion. In plasma it's plasma flame, HVOF it is oxy-fuel. In flame temperature it is 3000 to 3500 in case of flame spray, and 10,000 to 15,000 in plasma spray, 3000 to 3500 in case of HVOF. Gas velocity is below 300 in flame spraying, 400 to 500 in case of plasma spray, 1500 to 2000 in case of HVOF spray. In case of particle temperature, it is 1500 to 2200. In case of plasma spray, it is 2700 to 3500. In case of HVOF, it is 1500 to 2200. Particle velocity is 50 to 100, 100 to 200, and 600 to 800. Now thermal spray processes limitations. So in these there is lack of toughness. So in coating, the coating is not very tough and the coating thickness is also restricted. The bond strength is also limited and the application difficulties. So whichever process that it will be used, if it requires very high wear resistance, then it can be problematic. Welding surfacing. So these are various processes of welding surfacing. So gun tungsten arc welding, gun metal arc welding, shielded metal arc welding, flux cored arc welding, and submerged arc welding. Plasma transferred arc welding. Okay, and the thickness is around 6 mm. Okay, and there are various layers, first, second and third layers. Welding surfacing, this is the processing. So as you keep on forming a layer of another metal with the help of this uh, heat that is used from these sources that are told here. Okay, so in this case you have high deposition efficiency, you have low dilution factor, and you have good metallurgical bonding. Now energy density for different applications. Okay, so here you have log interaction time, have log power density. So based on these, there are these three types of processes: heating, melting, and vaporization. Another process is laser cladding, and it is shown for a particular laser. So this is IN718 microclad on SS304 with the plunger using pulsed laser. Then controlling wear. So these are various processes, and then deposition rate is told, and dilution percent is also shown for various processes. So for flame spraying it is less than 5%, for shield metal arc it is 10 to 30, and for flux core it is 10 to 30%, and for submerged arc it is 15 to 40%. And in case of this process, in case of manual metal arc, it is 1 to 3 kg per hour. In case of MIG, it is 2 to 6 kg per hour. In TIG, it is 1 to 2. In plasma transferred arc, it is 2 to 10. In submerged arc, open arc or strip cladding, it is 10 to 40. Okay, that's it from my side. So I'll just repeat the questions once again. Okay, I'll repeat the questions once again. Okay, so first question is, during the tempering process, the temperature of steel reaches up to, your options are below 650, 750 to 850 degrees Celsius, 1120 to 1150 degrees Celsius, 1200 to 1300 degrees Celsius. So correct answer will be below 650 degrees Celsius. So tempering is a heat treatment process which improves the properties of a steel by heating it to a temperature below its lower critical temperature and then cooling it gradually in the air. Purpose is tempering increases toughness, it reduces brittleness and improves machinability, and it's often used on metal products that will be under a lot of stress, such as bolts, nuts, screws, washers and knives. Temperature, the tempering temperature of steel can vary depending on the steel grade and the desired properties, but is typically between 160 to 600 degrees Celsius. Low temperature tempering is done between 150 to 200 degrees Celsius, which produces high strengths. High temperature tempering is done between 500 and 650 degrees Celsius. It produces microstructures which are more near equilibrium. Tool steels are tempered between 200 and 300 degrees Celsius. Spring steels are tempered between 300 and 400 degrees Celsius. Structural steels are tempered between 450 to 650 degrees Celsius. Process, the process involves heating the steel to a high temperature and then allowing it to cool in the still air. The cooling rate and method are important and usually involve cooling in air. Effect, the tempering process changes the steel's microstructure, which can affect the type, size and amount of carbides formed. Two-stage quenching of steel is carried out in the process called, your options are annealing, normalizing, martempering and ostempering. The process of quenching steel in two stages is called martempering, and it is also known as stepped quenching or interrupted quenching. Firstly, heating. Steel is heated above its critical temperature. Quenching, the steel is then quenched in a hot medium such as molten salt, hot oil or molten lead at a temperature of 150 to 300 degrees Celsius. And in this cooling, steel is then transferred to a less intensive medium such as air or oil and cooled completely. Okay, and martempering helps to increase impact strength, increase wear resistance, increase hardness, reduce the risk of distortion and reduce internal stress. So here cooling curve is shown. So up to here it is cooled, then it is held at this temperature and then quenched, then heated again for tempering and then again air cooled. Which of the following is true regarding the surface modifications? Your options are, the characteristics of the surface are different from the base metal, or increasing the life cycle of the component, or improved functionality of the component, or all of these. Correct answer will be all of these. Here we have surface modification is a process which changes the surface of a material to improve its properties or function, and there are several different surface modification techniques including plasma functionalization, where a single step process which changes the surface chemistry of polymers to improve their properties. Then chemical modification, which is a technique which focuses on the surface chemistry to improve the absorption of contaminants. We have CVD, which is a technique that deposits a solid layer of compounds on a surface by carrying out chemical reactions in a gaseous medium. Coating, it is a widely used technique which compresses the outer surface of a material to make it more resistant to breakage. Ion implantation, it is a technique which impacts accelerated ions into a solid surface to change its chemical or tribological properties. We have physical modifications. It is a technique which changes the topography or morphology of a surface without changing its chemistry. Have surface modification techniques which can be used in various fields including biomaterials, membranes and implant biomaterials. Next question is, which of the following are the processes used for the coating to preserve or improve material functionality? Your options are hot dipping, cladding, electroplating or all of these. So the correct answer will be all of these. And here you have schematics of hot dip galvanizing and electroplating. So in case of hot dip galvanizing, it involves dipping a metal object into molten zinc to create a thick coating that's resistant to corrosion, and the process is suitable for larger objects. In case of electroplating, it involves depositing a thin layer of metal onto an object using an electrolytic solution, and this process is better suited for smaller objects or those that require decorative finishes. Next is cladding. So cladding is a welding process which involves supplying a layer of weld metal to a base metal surface to improve its corrosion and wear resistance. It's also known as weld overlay, corrosion resistance alloy weld overlay or hard facing. Here you have schematics of hot dip galvanizing and electroplating. Fifth question is, the relation between carburized thickness and time in the carburizing process is expressed as. Your options are thickness is directly proportional to the time, or thickness is inversely proportional to the time, or thickness is directly proportional to the square root of time, or thickness is directly proportional to the cube of time. Correct answer will be C. So carburizing is a heat treatment process which makes iron and steel harder and more wear resistant by absorbing carbon, and this process involves heating the metal in the presence of carbon bearing material like carbon monoxide or charcoal at temperatures between 850 to 1000 degrees Celsius. Its benefits consist of, it creates a hard protective exterior while keeping the interior relatively soft, and this combination of hard exterior and soft interior makes carburized steel useful for manufacturing intricate metal items like internal machine components. Process tips, so carburizing often ends with the quenching the metal in a liquid to rapidly cool it and finalize the hardening process. And for a given steel at a given temperature, the depth of penetration is dependent on the diffusion and can be related to the time t by the equation K's depth equal to K under root T. Here K is a constant. The process of surfacing offers maximum metallurgical bond strength with the substrate, is your options are cold spray, HPOF spray, flame spray, or all of these. So correct answer will be cold spray. So cold spray is a surface modification process which creates a metallurgical bond with the substrate. In cold spray, solid powder particles are accelerated at supersonic speeds and they hit a substrate at a temperatures below the melting point, and the particles they deform plastically and they stick to the surface. Some of the benefits: it has several advantages over other thermal spray methods such as lower oxidation, less porosity, no phase transitions, no residual thermal stresses. And the materials: cold spray can be used on a variety of materials including metals, polymers, ceramics and composites. Applications: so cold spray is used for localized repairs and additive manufacturing. And here this is the schematic for cold spray process. Next question is: the arc spraying method results in a melted base metal depth of 3 mm and a surface layer depth of 2 mm. The dilution level ratio is, your options are 0.2, 0.67, 0.15 and 0.6. Correct answer will be 0.6. So dilution level ratio is given as depth of melted substrate divided by depth of melted substrate plus depth of surface layer. So it can be given as 3 by 5, which is 0.6. Next question is: which of the following processes causes surface layer deformation to improve the surface properties? Options are short peening, sandblasting, nitriding, and the options are 1 only, 2 only, 1 and 2, 1, 2 and 3. So C will be the correct answer. So in short peening, a cold process which uses steel balls to compress the surface of a metal, and this process is used to improve fatigue strength, and it can be used in the aerospace, automotive and construction industries. And short peening is different from short blasting, which is used to clean or prepare metals. In case of sandblasting, it's sometimes known as abrasive blasting, and it is the operation of forcibly propelling a stream of abrasive material against a surface under high pressure to smooth a rough surface, roughen a smooth surface, shape a surface or remove surface contaminants. It uses sand particles to remove material from a surface. Sandblasting is often used to prepare a surface for painting or coating. Nitriding is a surface hardening process which introduces nitrogen atoms into a ferrous alloy, and there are multiple nitriding processes which includes gas, plasma and salt bath nitriding. Ninth question is: step cooling in carburizing thermal cycle helps in reducing. Your options are tensile strength, hardness, cracking and distortion tendency, or all of these. So correct answer will be cracking and distortion tendency. From the maximum temperature, there is a step in cooling. Okay, so in a carburizing thermal cycle, lowering the temperature of a part before quenching reduces thermal stress and quench distortion, because overheating quenching directly from the carburizing bath can overheat the surface layer and lead to low surface hardness. And if the retained austenite is too high, the part may need to undergo a sub-zero treatment to transform it into martensite. Carbon content: if the carbon potential is constant, The carbon content and hardness of the part may drop quickly in the case, and this can lead to soft surface that can't be used. The range of flame temperature required in the HVOF thermal spray process is, your options are 1000 to 1500 degrees Celsius, 1500 to 2000 degrees Celsius, 3000 to 3500 degrees Celsius, or 10,000 to 15,000 degrees Celsius. Correct answer will be C. So the maximum gas temperature in HVOF thermal spray process is typically 3000 Kelvin. The powder particles are exposed to a flame in the combustion chamber, which melts or semi-melts them. The particles then enter a high pressure stream for spraying onto the substrate. And here the particle velocities are given as well as temperatures for these various processes. Temperatures are given in degrees Celsius. So for HVOF we can see it's around 3000. Now in case of heat treatment, so it can be defined as heating a material, then holding it at a particular temperature followed by controlled cooling. So controlled cooling meaning with controlled cooling rate. So it can be cooling can be in air, it can be furnace cooling, or it can be quenching in oil or water. Okay, so this gives you desirable mechanical properties, which can be better machinability, improved ductility, homogeneous structure, and desirable conditions such as relieving internal stresses. It causes relief of internal stresses developed during cold working, welding and casting, forging, etc. It hardens and strengthens metal, it improves machinability, and it changes grain size. It can soften metals for further cold working, as in case of wire drawing and cold rolling. It improves ductility and toughness. It increases heat, wear and corrosion resistance of materials. It can also improve electrical and magnetic properties. It can also homogenize the structure to remove coring, and it can spheroidize tiny particles such as those of Fe3C in steel by diffusion. These are some of the fundamental diagrams: iron carbon diagram, time temperature transformation diagram, and continuous cooling transformation diagram. Okay, so first we have iron carbon diagram. So here you have to remember these three reactions that take place: eutectoid reaction, eutectic reaction, and peritectic reaction. And the classification of steels based on eutectoid steel, hypoeutectoid steel, and hypereutectoid steel. And in case of cast iron, you have eutectic and hypoeutectic and hypereutectic. Then you are also given the soaking temperature ranges for the normalizing and full annealing and spheroidizing annealing. You also have time temperature transformation diagram, isothermal transformation diagram, and isotemperature diagram. Okay, so based on these three cooling curves, you can see there will be formation of different microstructures. And this is the continuous cooling. So here cooling curves won't be having isothermal cooling, which is holding at constant temperature during the transformation. So when it will be moving through the transformation curve, it will be continuous. These are various heat treatments. First we have annealing. So it is performed to reduce hardness, improve machinability, facilitate cold working, and produce a desired microstructure. Some of the types include full annealing, critical annealing, process annealing, and spheroidizing and stress relieving. Normalizing of steel is carried out by heating above UCT, which is upper critical temperature. It is this and this line, ACM and A3, and soaking there for some time and then cooling in air to room temperature. Aims to improve hardness and strength, to improve machinability. It forms fine perlite which has good machinability compared to coarse perlite, which will be in case of annealing. To modify the grain structure to provide more consistent response when hardening and case hardening. Then we have hardening. It is, in this case, the sample is heated above A3 or ACM to cause austenization. The sample is then quenched at a cooling rate which is higher than the critical cooling rate to avoid the nose of the CCT diagram. The quenching processes produces residual strains, thermal and phase transformation. So the transformation to martensite is usually not complete and the sample will have some retained austenite, and the martensite produced is hard and brittle, and tempering operation usually follows hardening. This gives a good combination of strength and toughness. Then we have tempering. After hardening, it is followed by tempering. Tempering is carried out by heating the steel below lower critical temperature and held for a period and then slowly cooled in air to room temperature. Okay, with increasing tempering temperature, we can see elongation increases, toughness increases and hardness reduces. Then we have Aus tempering and Mar tempering. These processes have been developed to avoid residual stresses generated during quenching. In both these processes, austenized steel is quenched above Ms to a temperature T1 for homogenization of temperature across the sample. In Mar tempering, the steel is then quenched and the entire sample transforms simultaneously to martensite, and this is followed by tempering. In Aus tempering, instead of quenching the sample, it is held at T1 here until the transformation is complete to bainite. Then you have these various processes with changing the thickness range and sizes. Okay. Then you have these various properties for tribological life. In case of physical properties, thermal conductivity, thermal insulation, thermal expansion coefficient, refractoriness, density, optical properties, where absorption and reflection of radiations is given. Then we have chemical properties, in which chemical affinity and corrosion and oxidation, these properties can be altered. In case of mechanical properties, hardness, strength, ductility, fracture toughness, bond strength, residual stress, corrosion, cracking, hydrogen embrittlement. And in case of dimensional properties, you have straightness, flatness, roundness, surface roughness and length, etc. These properties are altered. Okay, next we have surface modification methods, and the classification is based on whether there is some chemical changes or not. So first is change in surface structure or control deformation. So it can be based on thermal and mechanical. So in case of thermal, we have flame, induction, laser, electron, plasma and TIG arc. In case of mechanical, we have short peening and burnishing. Next we have change surface structure and chemistry. So in this case we have chemical methods at high temperature. We have diffusion based, in which carburizing, where there will be diffusion of carbon in surface. In nitriding there will be nitrogen. In nitriding we have diffusion of both carbon and nitrogen. In boronizing we will be having boron. In vanadizing you will be having vanadium. So in case of ion implantation, there is nitrogen and other elements are present. In case of alloying, we have laser, TIG and plasma. Surface modification methods. So it is used for developing a surface layer. And in this case we have options such as diffusion, CVD and PVD. Okay, a surface layer can be developed using CVD and PVD, or it can be developed using melting, which can be weld surfacing and laser cladding, or it can be using hot dipping, so zinc, chromium, aluminum and lead tin, or it can be using electrolysis. So in this case you have chromium and nickel, which is for aesthetics, cadmium and zinc for controlling corrosion, and copper and Ag for improving electrical properties. And there is hard chromium for enhancing wear resistance, and mechanical methods include roll bonding and explosion bonding. Next we have change surface structure. So in this case mechanical method, which is based on localized plastic deformation and so work hardening of near surface layers. It includes burnishing and short peening. In case of thermal methods, we have based on localized heating and controlled cooling to obtain desired microstructure. So in this case we have flame and induction hardening, and then we have laser and electron beam hardening, plasma and TIG melting. Next we have process comparison. So it can be, as you keep on going upwards, you see the processes will become more complex, and it will be also having more level will become higher in technology perspective. Now these are various fields of surface engineering. Then again we have mar tempering. So it is a heat treatment process for steel which involves quenching and tempering to achieve a uniform temperature throughout the material. The steel is heated above its upper critical point, and the steel is quenched in a hot bath of oil, molten salt or molten lead. The quenching temperature is slightly above the martensite start temperature. The steel is then held in the quenching medium until the temperature is uniform throughout. The steel is cooled in still air at room temperature. Mar tempering is also known as stepped quenching or interrupted quenching, and it's used to minimize distortion, cracking and residual stress. Mar tempering is well suited for high quality steels, bearings, gears, tooling, dies and shafts. Mar tempering is more expensive than other quenching or tempering processes because the quenching oils need to be specially mixed. Next we have Oss tempering, which is a heat treatment process which improves the mechanical properties of ferrous metals like steel and ductile iron. It's used to increase strength and toughness and to reduce or eliminate distortion. The process involves heating the metal to a temperature that produces austenite, holding it for a period of time and then rapidly cooling it to a temperature above the martensite start temperature. Oss tempering produces a banitic structure in steel and an acicular ferrite and Oss ferrite structure in cast iron. The Oss tempering is an isothermal process, so the transformation happens over time, resulting in uniform growth and less distortion. This makes it possible to design the dimensional change into the component, and the Oss tempered parts are ideal for use in systems that are under frequent stress, such as springs, clips, seat belts, loops, and agricultural components, lawnmower blades, mining oil and gas components. Then short peening. So it is a cold working process which uses high speed spherical particles to improve the surface of metal components. It has a stream of small spherical particles which are called shots are fired at a metal surface at high speed, causing plastic deformation. Short peening can improve fatigue performance, increasing resistance to stress corrosion, shape or strengthen the flat metallic parts, reduce component weight while maintaining mechanical strength, and expose and eliminate hidden corrosion. Short peening is commonly used on components like gears, springs, aerospace parts, drive shafts, crankshafts, connecting rods, steering and gear parts and turbine blades. There is a risk of weakening the component or reducing fatigue and bending strength. Test procedures have been introduced to prevent these risks. Okay, here you can see the shots and the formation of this compressive type of residual stresses. Okay, here the shot, they act like peen hammer, dimpling the surface and causing compression stresses under the dimple. The surface compression stress strengthens the metal. Sandblasting, sometimes known as abrasive blasting. It is the operation of forcibly propelling a stream of abrasive material against a surface under high pressure to smooth a rough surface, roughen a smooth surface, and shape a surface or remove surface contaminants. There are several variants of the process which uses various medias. Some are highly abrasive, whereas others are milder. The most abrasive are shot blasting with metal shot and sand blasting with sand. Moderately abrasive variants include glass bead blasting with glass beads and plastic media blasting with ground up plastic stock or walnut shells and corn cobs. The sand blaster components, which have a sand blaster which has a blast pot that holds the abrasive material and an air intake that's powered by a compressor. We have abrasive material. The abrasive material can be sand, glass, plastic, metal and walnut powder. Sandblasting process. the compressor applies pressure to the abrasive material in the blast pot, which is then forced through a valve and out of the nozzle at high speed. Surface impact. The abrasive material impacts the surface with force, removing debris, paint and other contaminants and improving the surface finish. So next is sandblasting is used on a variety of materials including metal, plastic and wood, and it's often used to prepare a surface for painting, epoxy or powder coating. Now these are various processes and which elements these use. So in carburizing, plasma carburizing, they both use carbon and mechanism is diffusion mechanism. Then we have nitriding and plasma nitriding, they use nitrogen element and use diffusion. And then we have cyaniding, carbonitriding and nitrocarburizing, which use carbon and nitrogen both and have diffusion process. Next we have boronizing, which has boron element and also uses diffusion. And we have laser, plasma, TIG alloying. So these all use chromium and nickel and they use melting mechanism. Ion implantation uses ions and mechanism is damaging crystalline structure. Next is hardness versus processes, and here with increasing hardness we can see lowest will be in carburizing, then we have carbonitriding, then higher than that we have nitriding, and then highest will be boronizing. The hardness of steel and titanium carbide is also given for the comparison. And this is the approach for these various processes, diffusion based processes. Here you have rich environment for nitrogen, chromium, carbon and boron and silicon. So this will diffuse in the surface area, so the concentration will keep on decreasing as you move far away from the surface. Okay, so in carburizing you can see this is the carburized layer and you have ferritic matrix. So matrix will be tough in nature, while this carburized layer will be providing very high hardness, wear resistance and corrosion resistance. Then the carburizing depth, it also depends on the temperature of carburization. So at 950 you will be getting higher case depth at a same carburizing time. Hardness versus carburizing depth. So with carburizing depth you can see hardness will decrease and carbon weight percent will also keep on decreasing, and residual stress will be lowest near the surface and it will keep on increasing up to certain point. Okay, and this is the schematic for carburizing. Okay, that's it from my side.